Hello everyone, welcome back to my channel. I hope everyone is preparing well for their JEE Advanced exam, which is just a month away. And to all of those students who have cracked JEE mains and have excelled and cleared the cutoff for the JEE Advanced exam, my best wishes to you. So keeping that thing in the mind, we are bringing a lot of questions to you which are relevant to the JEE Advanced exam and which will be definitely helpful to you in acing the exam, right? So in the view of that, we have this question, which is a very interesting one, which belongs to organic chemistry. Now, this question involves a lot of topics. There are a lot of interesting topics and a lot of interesting concepts here, which will be clarified as we go through the question, right? So, just let's have a look on it. Now, the question says we have a compound X and we are heating it in the presence of aqueous NaOH for a long time. In the second step, we are adding the H plus. It gives A. Now A in the presence of sodium boron hydride, which we know it's a good reducing agent, will give you B and C, which further in the presence of H plus and the warm conditions give D and D. That is about the story of reaction of X, right? Next is the reaction of next compound. Just a second. Yes. Next compound is basically alpha hydroxy, alpha keto acid, right? So reaction of this compound with the sodium boron hydride gives FNG, which on further in the presence of acidic medium in warm conditions give three compounds HING. Now a little bit hint is given in this question to proceed further that A is an open chain compound, that A compound which is formed from X is an open chain compound, B and C, D and E, F and G and H and I are enantiomers, right? That means this pair B and C which is formed and D and D is formed, F and G is formed and H and I are formed. They are enantiomers of each other. Whereas if you see here the three products are formed all together, H, I and J, where H, I and J all three are stereoisomers. All three are stereoisomers, right? So before going to the options and before going to the questions, let's try to solve the problem first. Let's try to bring the compounds which are formed here in the reactions so that we can have the quick idea of how to match the column. Now if you look at the question, the reactant which is given to us is this one, right? This is the reactant which is given to us. Now the question says this reactant is reacting with sodium hydroxide for a prolonged amount of time. Now if you look at it, in this molecule we have two sites where alpha hydrogens are present, right? But the point is, even if we remove the alpha hydrogen, I don't see any way this reaction proceeds further. So in this reaction, what will happen? There will be a nucleophilic attack. Now OH minus is basically what? OH minus, which is obtained from NaOH, is a nucleophile, and this nucleophile will be attacking the electrophilic site. And electrophilic site here for us is this carbonyl carbon as well as this carbonyl carbon. Since the molecule is symmetrical in nature, right? This molecule has plano symmetry, that's why it is symmetrical. So this OH minus can easily attack at any of the site. So let's say this OH minus attacks on the electrophilic carbon on this site. So once it attacks happens, the upper O will take away the pi bond, and in this reaction, what will happen? In the first step, we will obtain this intermediate, right? Now since the O has obtained the minus charge, which is unstable in nature, because we are using the basic medium NaOH for a very large amount of time, so there is no available H plus ion right now to neutralize the O minus. So that means O minus is a negative state, that is in the charged state, which is an unstable state. Now because it is an unstable state, what will happen? This negative charge will go back to make the double bond like this, but the moment it will go back to make the double bond, this carbon will become the pentavalent, which is not possible. So that means one of the carbon-carbon bond has to be broken. Now here, interesting point is that which carbon-carbon bond is to be broken, or which carbon-carbon bond we should break, right? So if you look at it, we have C1, let's say this is C1, this is C2, this is C3. Now if we break C1, C2 bond, right, what will happen? the C1 will attain the negative charge, because what will happen if this electrons of negative charge of oxygen comes back like this. Let's say this is a step 1, and let's say this bond is there, right? C1 C2, these electrons will come back to carbon 1, so carbon 1 will get the negative charge. And if the carbon 1 gets a negative charge, there is no way it is getting stabilization, right? But if we break the 2,3 bond, if we break C2C3 bond, what will happen? The moment we break C2C3 bond and these electron pairs comes back to the third carbon, there is this carbonyl group available here on the adjacent carbon, which will easily stabilize the negative charge through electron withdrawing tendency, right? So that means when the negative charge of oxygen from first step, that is from the step 1 here, will go back to make the double bonded oxygen, C2C3 bond will be broken. So once we break the C2C3 bond, the further product obtained is this one. So what will happen here? Let's say we have the double bond like this, and OH is here, so it will be something like that. Here double bond O comes, and this carbon will get the negative charge like this, right? After that, what will happen, since we have the acidic medium, the H plus is available in the second step. This H plus will go and neutralize the negative charge formed. That means the compound which we obtained here is the carboxyl group, and then we have the carbon, carbon, and carbon. Next carbon has C double bond O, and next we have CCH. This is the molecule which we have obtained, right? So this is the A molecule. This is the A molecule which we have obtained from this reaction, right? Now, what to do? The A molecule has undergone the reduction. You are using the sodium boron hydride. So if we do the reduction of A molecule by using sodium boron hydride, just a second, right? If we do its reduction by using NaBH4 in the presence of ethanol, basically NaBH4 reacts in the presence of an acidic medium, right? But that, or we can say protic solvent, and that protic solvent H plus ion is available in the second step. And since C2H5OH is also a protic solvent, that is why we are using it. Now here what will happen? NaBH4 is a reducing agent, and we know it reduces only aldehyde and ketones. It doesn't have any impact over the carboxylic group. So that means the carboxylic group will remain same, and here we will obtain this keto group will convert into hydroxy group like this, right? So this is our molecule. Now this molecule, if you look at it, in this molecule we have obtained from A to B and C. Now here we have a chiral center. This is the chiral center. Because it is a chiral center, that means two enantiomeric pairs will be formed, or we can say two enantiomers will be formed, right? Either R or S. So that is why the two compounds B and C are there. Also the hints are given that compounds B and C will be what? They are enantiomers of each other. So that is how we have obtained the B and C. So this molecule is either B or C, right? This is what we have obtained in the terms of their stereochemistry. Next step is what? In the next step, the product obtained, that is B or C, is made to react in the acidic medium under some warm conditions. Now if you look at this molecule, in this molecule we have one carboxylic group, right? We have a carboxylic group, and along with the carboxylic group, just a second, along with carboxylic group we have also hydroxy group. Now since we have the carboxylic group in the same molecule and hydroxy group in the same molecule, and the conditions are acidic in nature, what will happen? The esterification reaction will take place, right? And in the esterification reaction, what will happen? By, instead of going in deep into the mechanism, which we will cover in the separate video, where we will exclusively discuss about the esterification reaction and its conditions, what will happen? Cyclic ester will be formed. See, the molecule, this reaction will be what? This reaction will be intramolecular reaction. Intramolecular esterification reaction, because within the molecule we have the OH group and within the molecule we have COH group, right? So now what will happen? In esterification we know there is a loss of water molecule and this water molecule is lost. Very important thing to remember that in the formation of this ester, let's first make it, then I will discuss. Now here we have to check how many membered ring will be formed, right? So if you look at it, 1, 2, 3, 4, 5 and 6. There will be a 6-membered ring, so let's draw it. And oxygen comprises that 6-membered ring, right? So it will be something like that. Now if we remember the oxygen as first compound, or we can say first element, if we in that case what will happen, let's say the oxygen is first one. So oxygen is attached to which carbon? 6 carbon. So let's say this is a 6 carbon. So it is 5, it is 4, it is 3 and it is 2, right? Like this. And the second carbon contains this bond, like this. So this is how we obtained it. And the 6 carbon contains double bond O, like this. So this is the molecule which we have obtained finally. Now if you look at it, it is a kind of cyclic ester, right? It is a cyclic ester available to us, and the cyclic esters are also called lactones. Lactones is the common name for cyclic ester, right? And if you look at the cyclic ester, again at the C2 carbon, if you look at the C2 carbon, it is chiral in nature. The C2 carbon is chiral center here, or we can say the chiral carbon. And this molecule possesses no plano symmetry, no central symmetry. That means it is optically active in nature. This molecule is optically active in nature. So this is how we have finished the first reaction, where by using the reactant X we have obtained the products D and D, right? Here also again, because it is optically active in nature, so it will be obtained in the form of enantiomers. That is why this compound comprises of 2 parts D and E, right? Now next the molecule which we have is the alpha keto carboxylic acid, this one, right? In this molecule, now this molecule is there. If you look at it during the reaction, first of all we are doing the reduction of this molecule by using the sodium boron hydride and C2H5OH. So again we know when we do the reduction by using NaBH4, the keto group will be reduced to the alcohol, whereas the carboxylic group will remain unaffected, right? So in that case the product obtained will be this one, alpha hydroxy carboxylic acid. And the alpha hydroxy carboxylic acids are basically what? This is basically also called lactic acid. It's a kind of, or we can say it's the formula of lactic acid. Here also if you see, this is the chiral center. Now because it's a chiral center, again we will have the enantiomers. That is why after the reaction of this molecule with sodium boron hydride, we have obtained F and G, and F and G are enantiomers of each other as given in the hint in the statement. So again we have F plus G obtained here, right? Once we have obtained F and G, next is what? Next again, in the warm conditions, in the presence of acidic medium, we are obtaining the 3 products H, I and J. So let's say how we obtain this thing. Now here if you look at it, we have obtained the alpha hydroxy carboxylic molecule, and this molecule, within the molecule we have OH group as well as carboxylic group. So one thing should click to us is that we can do the intramolecular esterification reaction. But remember this thing, that in the above example, in the above reaction, once we have done the intramolecular esterification reaction, we have to take care of the ring size also. In the above example, this one which you can see here, we have obtained the 6-membered ring, and the 6-membered rings are generally considered stable. That is why this intramolecular esterification was favorable, and we have obtained the cyclic ester, that is lactone. If you try to do the same thing in this molecule, that is alpha hydroxy carboxylic acid, that, or we can say F or G, we will be obtaining a very small sized ring, right? It will be comprising of 3 members, right? and having a ring of 3 members will not be a safer option, or we can say it will be highly unstable in nature, correct? So because we know generally the stability of the rings, if we could talk about the ring size stability, generally 5 member ring or 6 member ring is highly unstable in nature. Below 5 member ring the stability keeps on decreasing, and since in this case, in this molecule, if we try to do the cyclization through intermolecular esterification, the ring size will be very small. So what do? We will utilize the two molecules. We will utilize the two molecules of it and then perform the trans esterification, or we can say cross esterification. So what will happen? Let's say we have this first molecule. This is our first molecule, and the second molecule is again we can draw in a similar way. Let's say we have this our second molecule, and I will be drawing it this way, right? Like this. I'm drawing it in a reverse sense so that we can easily visualize the reaction formation. Now, just like we have done the esterification above, where OH from the carboxylic group and H from the OH group are lost, that is H2O is lost, and the cyclic ester is formed or cyclization has taken place. Same thing will repeat here. Here also, just a second. Here also we'll do the same way. The OH group here we have, and the OH group here we have. So we'll do one thing. Here, the hydrogen from the upper OH group, let's say it is like this, right? So OH from the carboxylic acid and H from the upper group will be removed like this, right? Similarly here also, OH from this upper carboxylic group and H from the lower molecule will be removed like this, right? That means two water molecules are removed. We have removed two water molecules, and if you look at it, after removing the two water molecules, there will be a proper cyclization that is occurring here, right? There will be a cyclization of molecule, and if we draw it properly, let's say, let's draw it. Let's start with this carbon, right? And this carbon is, let's say, this one, which contains oxygen. And once it contains oxygen, so the carbon adjacent to it contains double bond O, and then we draw it further. We make it it is making the bond with this oxygen. Let's say this is O1 and this is O2. So this is O2, this is O1, right? Like this. Now further, with adjacent to O1, we have this carbon, right? Let's number it so that you can easily visualize how we are making the product, right? So let's say this is the fourth carbon and this is the third carbon. So third carbon is this one and double bond O. Just a second, little bit mistake. Right, now it makes a bond like this in this way. So this is the fourth carbon, right? And here we have like this. So this is how we obtain the product from this reaction. Now here, if you look at it, we have obtained multiple cyclic esters within the same molecule, right? There are two cyclic esters which we have obtained. One is this one. This is a cyclic ester. This is also a cyclic ester, right? Through the intermolecular reaction, intermolecular esterification. Whenever the intermolecular esterification takes place and we obtained cyclic product, right, which contain multiple cyclic esters, that is lactones, such products are called lactides. Let me try it again. These products are called lactides, right? So just a second. Mhm. This is what we have obtained. This is called lactide. Now, since we are dealing with the stereochemistry also, so we have to check whether this molecule will be having multiple isomers or not. So here in this case, what will happen? Since if you talk about this carbon and this carbon, these carbons are what? These carbons contains chiral centers. So because they contain chiral centers, we can have multiple isomers formation here. Let's draw the multiple isomers. In first case, what can happen that here this CH3 group and this CH3 group will be wedge and dash. This is the first part, A molecule. In second case, what can happen, like this, both CH3 groups will be wedge, this is B, and in third case, both CH3 groups will be dash, right? This is the third molecule. Now if you look at first, second and third molecule, in the first molecule A, we have the center of symmetry, right? The molecule A possesses center of symmetry. That's why the molecule A is optically inactive. And also because it contains center of symmetry, it is optically inactive. Therefore, it is a meso compound. It is a meso molecule, hence it is optically inactive in nature. And if you look at B and C, there is no centrosymmetry, there is no planosymmetry in B and C molecules because there is no COs, POC or SCOS, right? They are optically active in nature. So B and C both are what? Optically active molecules. Now if you look at above here, from F and G, that is after their reaction with H plus in the warm conditions, we had obtained three products, H, I and G, right? Where H and I are isomers and H I and J are isomers and Hij are stereoisomers, right? So that means here, when we are talking about isomers, that is enantiomers, B and C are enantiomers. These B and C are basically H plus I, that is H and I. And this molecule is basically J, the optically inactive one, that is the meso compound, right? So this is how we have obtained the reactions. I hope you have understood how to do the reactions of this question, right, which are available here. Now let's go to the main part that we have to go with the questions available here. Now let's go to the first question. First one. The only correct option, the only correct combination from the among the following, we have to find which one is the correct option, right? First one. If we talk about option A, fourth, second, and Q. Now the fourth one is what, J, right? And second one, lactide. J is basically not lactide. J is basically, yes, J is, just a second, J is lactide also, right? J and second are correct. And second, it goes to Q. Now Q is what? Q says that it possesses S2. S2 is basically alternate axis of symmetry, right? Second alternate axis of SN, or we can say S2 alternate axis of symmetry. Now how to find the alternate axis of symmetry? Let's try to do it. The compound J which we have obtained here is this one. This question is going to be a bit lengthy, but I hope you will understand and you will learn many new concepts here to apply. Now this is our molecule, right? This is our molecule. In the case of J, we have to try to find the alternate axis of symmetry and see whether it possesses any alternate axis or not. So what do? We'll do one thing. Just a second. Let me check, are we doing the same reaction or not? We're talking about the fourth one. Fourth one is J, right? And the J is right. Now in this case, what to do? Let's say we have this molecule. Whenever we have to find the alternate axis of symmetry, so do one thing. First of all, try to rotate this molecule around any particular axis, right? So let's say we have this axis, we are talking about this axis. Let's say along this axis, I'm trying to rotate this molecule like this. Let's say I rotate it by 180 degree. So if I rotate this molecule around like this axis by 180 degree, what will happen? Upon rotating it, I will obtain the molecule in this way. The oxygen will go here, right? And double bond will come here like this, and here the double bond will come, here oxygen will come. Here in this, at this carbon, we have the CH3 group at the wedge position, dash position, it will become wedge, right? And upper one will become dash. Now once we have rotated around a particular axis at a particular angle, right, now try to find the mirror image of this obtained molecule. Let's say the original molecule is A, capital A, and the rotated molecule is B. Now try to find the mirror image of molecule B at an angle or at a plane perpendicular to the axis at which we have rotated. So if you look at the question here, if you look at your own screen, this is the axis, right? This is the axis around which we have rotated it, right? In a way, we have flipped the molecule, right? So the plane which we have to check about is this one. This plane is perpendicular. This plane is perpendicular to the axis of rotation. And if you try to draw the mirror image along this plane, let's see what do we obtain. We obtain the molecule like this, and here the oxygen comes, here comes the wedge, here comes the dash, and at the farther side we have like this, right? This is C. Now if we have to check whether this molecule contains any alternate axis of symmetry Sn, the original molecule and the molecule obtained as C must be similar in nature, right? Must be similar in nature. But if you look at A and C, the position of the groups is same, right? The position of groups is matching, but the stereochemistry is not. On the upper carbon, the methyl group in the C is dash, whereas the upper carbon methyl group in A is wedge. That's why they are not matching, and hence the molecule doesn't possess any alternate axis of symmetry, right? That means option A is incorrect. Option A goes to be incorrect. I'm trying to explain all the options one by one just so that you can have the proper in-depth knowledge of the concepts applied in this question. So I'm again saying it's a little bit lengthy question, but too much informative for you to clear your all the doubts. Second option, fourth, second, P. Now fourth, second, again second is there, and P. P is what? It possesses zero chiral center, which is again incorrect, because if you look at it, yes, okay, just a second, fourth, second, P. P says it possesses zero chiral center, which is correct because the molecule is what? Molecule is optically active in nature. So here only we have, sorry, molecule is optically inactive in nature. The J molecule, if you look at here, J molecule is optically inactive because it is meso compound. Since it is meso compound, it is optically inactive, and hence the correct answer of ours is option B, right? So first question is done. Second question says the only incorrect combination among the following. So let's try to find out. Now the first option is 4 second R. 4 is J and second is lactide. Again, fourth one is J is lactide, and R, it possesses centrosymmetry. It possesses centrosymmetry. That is correct, right? We have already written it that the J molecule is optically inactive because it has COS. It has centrosymmetry. If you look at the J molecule, from the center of it, what do? We try to connect the same type of molecules through the imaginary line, right? If you try to connect this O and this O, then we have to connect these ones, and here in this carbon, the upper one, the wedge part is methyl, and the lower carbon, the dash part is methyl, and from here to here, if you connect all the molecules, all the elements, all the atoms in this molecule are passing through the common point, that means it contains COS. So it do contain COS, that means option A is correct. Option B, third, second, S. Now third one is what? H. H is not lactide. Sorry, H is also lactide. The third, second is correct. S. It do not possess any element of symmetry. Right? That is also correct. It doesn't possess any element of symmetry. H1. That is why H is what? H and I are optically active molecules because they don't possess any element of symmetry. Next, C. Third, fourth, and S. Third is what? H, and fourth one is optically active. That is correct. S again correct because it is having no element of symmetry. D1, second, third, and Q. Now second is what? Second is X, and X third. That X is there, right? That is the reactant only. X means the reactant only. The first one. Its combination is with third. Third statement says it reacts with NaBH4 and C2H5OH. Correct. it do reacts with that one, because if you look at it, we have ketone part here, right? In the reactant we have the ketone, and the ketones easily reacts with sodium boron hydride, NaBH4. So yes, here D, second and third, right? Second and third is correct. Final is Q. Q says that it possesses S2 symmetry, right? It possesses S2 symmetry. So let's do one thing again. Let's try to find out whether it possesses S2 symmetry or not. Now the molecule is like this. This is the molecule which we have, right? Now do one thing again. Let's try to rotate the molecule. Let's try to rotate the molecule to find whether it possesses axis of symmetry or not. So when you rotate it, let's say along this axis, right? Now this axis is like above the screen and below the screen, right? If you can imagine it, it's good. This axis will be like above the screen and below the screen. Let's try to draw it in a stereo manner like this, right? Along this point, if we rotate it by 180 degree, let's say I rotate the molecule along this point by 180 degree. So what will happen? Upon rotating it, the rotated molecule, let's say this is x, small x, upon rotating it, the one which we obtained is like this. The double bond O comes here, and this double bond O comes here, and here the wedge and dash both remain same because both are CH3, right? So this is the rotated part. Why? Now since if you see the angle of rotation, the axis of rotation is perpendicular to the screen, right? Now we have to check the mirror image of this molecule along the plane which is perpendicular to the screen, right? That is perpendicular to the axis, right? So if the line is perpendicular to your screen where you are watching, the axis where we check, or the plane which we check is this one. Along this plane we have to take the mirror image, right? If you take the mirror image of this molecule along this plane, it will come out to be like this. It will be, yes, like this. This is Z. Now if you compare X and Z, are they equal? Are they similar? No. X and Z are not similar to each other, right? X and Z are not similar. So if they are not same molecules, that means no SN, no alternate axis of symmetry, right? So here, if you look at it, the question says the only incorrect statement here. Second, third, Q. J is what? Second means X, and third, yes, we have proven that X reacts with third. And Q is what? Q, it possesses S2 symmetry, which is incorrect. So here the option is D, right? Next statement is what? Next question is third one. The only incorrect combination among the following, right? Again, the same thing, incorrect combination we have to find. Second, third, and P. Second is X, and it reacts with third. Yes, we have proven it. And P, it possesses zero chiral center, which is correct, because if you look at the reactant above, this reactant X1 has what? It contains plane of symmetry. Now, because it contains plane of symmetry, it is optically inactive in nature, right? So A is correct. B, first, second, S. First is D, right? D is what? D is lactone, which we have obtained. Let me just show it to you. This one, the D is the lactone which is obtained. The question says D, and the first one is D. Second is lactide. No, second is actually what? This combination is not correct. This combination, if you talk about this combination, 1 second and S is not correct, because one is what? One is basically lactone, not lactide. So it is the incorrect combination. So this is how we solve this problem. I know this problem took a lot of your time to understand, but trust me, with the patience which you have used to watch this video, I hope you have gained a lot of information from this video, which you can easily apply in your following questions, which you will be seeing on this channel again and again. So I hope you have understood this concept very well. If you like the video, please do like it, share it, and spread your love by subscribing the channel. And let's connect back, and I'll bring you a lot more questions like this. Thank you. Have a nice